Welcome to the flight deck, everyone. I'm absolutely thrilled to have you here for this explainer. Today, we're conquering Earth geometry and coordinates. Now, if you're gearing up for your DGCA Commercial Pilot License Air Navigation exam, you already know this is one of the most rigorous, mathematically demanding subjects you're going to face. But hey, don't sweat it. We're going to break the whole thing down perfectly.
We've got a really solid roadmap today. We'll start by building the core concepts from scratch, dive into the exact formulas you need, expose some of the DGA's favorite trick questions, and then wrap it all up with a rapid-fire review. Let's get right into it.
All right, picture this. You're commanding a heavy jet, flying from Europe to the US West Coast. If you just glance at a standard, flat map, you'd probably think drawing a perfectly straight line from your departure to your destination is the most fuel-efficient path, right? Well, it actually isn't. That perfectly straight line on paper is somehow longer when you're actually up in the sky. So why is that?
To answer that, we really need to understand the Earth's grid.
First things first, the Earth is not a perfect sphere. Since our planet is constantly spinning, it generates centrifugal force, pushing its mass outward. That force is zero at the poles, but at its maximum right at the equator. This creates what we call an equatorial bulge and polar flattening. So, the shape is actually an oblate spheroid. And for modern aviation and GPS systems, this specific shape is mathematically modeled as WGS84. Keep that term in your back pocket.
Now, to navigate this oblate spheroid, we need reference lines, the graticule. First, we have great circles, which literally slice the Earth into two perfectly equal halves. The equator is a great circle, and so are the meridians of longitude that run from true north down to true south. On the flip side, we have small circles, like the parallels of latitude, which do not cut the Earth into equal halves.
Here's where that squashed shape really matters. Latitude actually has two different definitions. Geocentric latitude is measured strictly from the exact geometric center of the Earth, but geodetic latitude, which is also called geographic latitude, is measured perpendicular to the actual surface you're standing on. Because the Earth is flattened, a line drawn perpendicular to the surface doesn't perfectly intersect the Earth's center. And here's the key takeaway. Geodetic latitude is the one used for literally all mapping, coordinates, and aviation charts.
Okay, so let's think back to our flight from Europe to the US. This is how a great circle and a rhumb line actually behave on a 3D globe. That dashed line, that's your great circle. It is absolutely the shortest physical distance between 2 points on a sphere, saving you time and precious fuel. But notice how its true direction is constantly changing. Then you've got the solid line, which is the rhumb line. It's physically a longer path, but it cuts across every single meridian at the exact same angle. So if you're steering a constant heading of, say, 270 degrees the whole way, you are flying a rhumb line.
Now, while we're navigating this grid, our compass doesn't always point exactly to true north. We have two very specific errors we have to account for: variation and deviation. Variation is simply the angular difference between true north and magnetic north, and that's caused entirely by the Earth's own magnetic fields. Deviation, on the other hand, is the error caused by the magnetic fields inside your own aircraft, like your radios and electronics, literally pulling the compass needle away from magnetic north.
All right, let's transition from the concepts to the actual math.
We're going to tackle a classic geodetic shape problem. Let's say you're given an equatorial radius, the semi-major axis, which we'll call A, of 6,420 nautical miles. The compression ratio of the spheroid is 1/280. You need to find the polar radius, or the semi-minor axis, which is B. Here is exactly how you do it. The formula for compression is F equals A minus B all divided by A. We know F is 1/280, and A is 6,420. To isolate our unknown B, we just rearrange the formula to B equals A multiplied by 1 minus F. Plug in those numbers. B equals 6,420 times 279/280. Run that through your flight computer, and boom, you get a polar radius of approximately 6,397 nautical miles.
Next up is Earth convergency. This is the angle of inclination between two meridians at a specific latitude. The formula is straightforward. Earth convergency equals change of longitude multiplied by the sine of the mean latitude. In plain English, you find the exact middle latitude between your 2 points, take the sine of that angle, and multiply it by the total degrees of longitude you crossed. But listen to me carefully right now, because this is where students constantly mess up. You absolutely must convert your degrees and minutes into decimal notation before punching them into your calculator. If you just type minutes in as decimals, your answer will be totally wrong and you will lose easy marks.
Now that we've got the math down, let's put on our exam hacker hats and look at some classic DGCA traps.
Here is a super common multiple choice trap about the 180-degree anti-meridian. The question will ask,
What is the direction of the shortest change of longitude track from 175 degrees east to 175 degrees west? And of course, you'll see options for east, west, north, and south.
So, how do we avoid this cognitive trap? Your brain sees the W in 175 west and instantly wants to click west. But think about it. If you are at 175 east, you are only 5 degrees away from the 180-degree line. Going east across that anti-meridian takes a mere 10 total degrees of travel. If you flew west instead, you'd have to fly 350 degrees around the entire planet. The shortest path is undoubtedly eastward.
Let's look at another one. Remember our chat about the 2 types of latitude? Well, the DGCA loves to force you to recall the exact latitude where the Earth's oblateness creates the absolute biggest angular discrepancy between geocentric and geodetic latitude.
I want you to lock this number into your memory right now. 45. The maximum difference is exactly 11.6 minutes of arc, and it happens right at 45 degrees latitude. Down at the equator and up at the poles, that difference is 0.
Now, to build your intuition for those tricky map questions, how do you remember which way a great circle curves compared to a rhumb line? Just memorize this golden little quote. Mr. Mercator lives in a cave on the equator. This mnemonic is a lifesaver. It instantly reminds you that great circles are always concave to the equator, meaning they always curve toward the nearest pole. Meanwhile, rhumb lines always sit closer to the equator.
Okay, time for a final sprint before you hit the exam hall.
Fire these 4 facts right into your short-term memory. Number 1, the Earth is an oblate spheroid mathematically modeled as WGS 84. Number 2, geodetic latitude is greater than geocentric, and their maximum difference sits right at 45 degrees. Number 3, great circles are the shortest distance and curve towards the poles, while rhumb lines give you a constant heading. And number 4, to apply magnetic variation, remember variation west magnetic best, meaning you always add westerly variation to your true heading.
And just like that, you have the fundamental geometry of the Earth completely locked down. But remember, knowing the theory is only half the battle. Applying it is how you actually pass the DGCA CPL exams. Your next logical step in the syllabus is time and time conversions, which builds directly on these longitude concepts. Until then, keep climbing. Head straight over to clouddeck.in right now to practice these exact MCQ types in their exam simulator. How well can you spot those DGCA traps when the clock is ticking down? That's the real test. I'll catch you in the next experiment.